Good afternoon. My name is Kendall Standridge Monroe. I greatly appreciate the opportunity to present my research here at the International Symposium on Digital Forensics and Security. I am currently in the Engineering Management Graduate Program at the University of Tennessee at Chattanooga with a concentration on the power industry. My co-author is Dr. Asaf Farol. And with that, I present optimizing resistive losses in transmission systems via voltage level selection. For this presentation, I'll start with a brief overview of the U.S. power grid. We'll talk about Ohm's law and how it relates to power loss, some key trade-offs in designing an engineering transmission system, the research objective of developing a model to address this, the methodology behind that research model, the results, and then I'll wrap up with a discussion and a last conclusion. The U.S. power grid really starts with generation, where power is made from, a coal plant or a nuclear power plant, solar panels. The generation methods are varied and far between. But once that power is generated, it goes through a substation where the voltage is stepped up. Then it is transmitted via transmission lines, and that's really where our focus is today. When it gets a little bit closer to point of use, that voltage is stepped down at another substation, where then it is sent through distribution lines to the end point of use, the residential or commercial areas, industrial. So that transmission line is really where we want to focus on. And the first time that I had the power grid explained to me, the question that stood out is, why would we step it up just to step it back down? And the answer to that really lies in Ohm's law, which we will talk about next. So Ohm's law is described with this first equation. Voltage equals I, which is the current, times R, the resistance. And power loss, P, equals voltage times the current squared. So efficiency loss is primarily driven by the current increasing. But if you can keep your current low, then you're going to lose less heat to the environment. So transmitting power at high voltages reduces that current, which in turn reduces the generated heat. So if you think about it, the higher voltage equals a lower current. The lower current equals less heat loss. Less heat loss equals more energy transmitted from point A to point B on that transmission line. And more energy transmitted should equal a cheaper energy cost, or at least less of energy lost to the environment that can't be recuperated from a cost perspective. If efficiency and the heat loss were the only things that needed to be considered, then it would be simple. We would run 500 kV lines all over the place. That would be the only voltage that was transmitted, and it would be a done deal. That's not how the world operates, and as with most things, there's key trade-offs in transmission line design. So as voltage increases, yes, the resistive losses are reduced, but with that, the tower height increases, the air gap and insulation needed to maintain safe operation of those transmission line increases. The right-of-way around the structures and the line increase. Conductor size and weight also increases. And with that, the structures to support this line material become more bulky, more labor-intensive to design and build. And overall, the cost to build and maintain these structures also increases as voltage increases. Clayton and Grant in 1987 developed this model to basically show that there's a sweet spot where the optimal cost is balanced between energy loss, capital cost, and maintenance. So with that background in mind, my research objective was to develop an Excel solver optimization model to determine the most economical transmission voltage. The goal was to take into account the resistive losses from heat, but also the cost impact to building this transmission line model. So the model took into account 4 different power levels: 10, 50, 150, and 400 megawatts. It also took into account 3 different line lengths, so 60, 110, and 160 kilometers. For conductor selection, 40 common conductor types were used. These were types of ACSR and AACs, the most common that are used in the industry. The conductor material was broken down in a cost by kilometer reference, and then the 10-year power loss was estimated based on the given factors for each time the model was ran. Average structure costs were also brought in as a parameter. So the material, the design, the manufacture, delivery, installation, basically all of the components that go into determining what the structure would cost at the end of the day. These were estimated using the MESO references from 2025. And then an additional constraint was built in. There are minimum conductor size requirements at different voltage levels, and it changes whether it's an ACSR line or an AAC line, and it also changes given the different voltages. So this constraint was built in as well. To establish the solver model, I started with establishing a reference table of 40 different conductors, common conductor types that information was readily available on, and building out a table to compare size, resistance, and then doing some calculations to get a price per kilometer of that conductor material. I kept the conductors with their standard code names. They're all named after typically birds. And I kept that as the name factor for each conductor. I also built an Excel solver model to input the variables of voltage, power, and line distance in order to calculate the power loss, and then through that, an estimated 10-year cost of power loss at those settings, cost of the conductor material per kilometer, and then the structure cost. And this estimate is based on the estimated structure cost at the different voltages, as well as the number of structures per kilometer at those voltages. And so that those two parameters came together to give an overall structural cost estimate. Next, I built in constraints for a minimum conductor size requirement. So basically setting it up so as the voltage level varies, any of the conductors that do not meet that minimum size requirements are excluded from the pool of feasible conductors that are able to be selected. So this prevents misuse of selecting a conductor that feasibly wouldn't work in the field. Next, I ran the model for each power and line distance combination to really just see how it functions and to gain some insight into those parameters. So this is an overview of my solver model. Columns K through T are changed based on the distance and the power and the voltage that is entered in, and then the most optimal of the table that's built based on the voltage that's provided will be highlighted in red. Now the voltage that is provided is changed by the solver model when it runs based on selecting which voltage would produce the most optimal solution. So in this case, this value here in C55 goes from 1 to 7, with 1 representing 69 kV and 500 kV being represented by 7. And the variables input are the kilometers and the power that needs to be transmitted. So looking at the first example of 60 kilometers and 10 megawatts, we will run the solver model. And it quickly gives us a value of 230 kV as the most optimal solution, and the total cost is 20.59, and that's in millions. So that cost takes into account the structure cost based on the number of structures per kilometer and the average structure cost for each voltage. It also takes into account the conductor material per kilometer, the cost for that. And lastly, it takes into what 10 years of power loss would be estimated at for these parameters here, this 230 kV line with this distance and this power rating. So let me change to another variable here. So we'll go 400, take me back to 69 kV as a starting point. I'm going to run my model again for 60 kilometers and 400 megawatts. And when I do this, you can see that it changes my optimal voltage now to 500 kV and 44.98 millions as the total cost estimate for that. Now, for this model and for, proof of concept, I limited it to, 4 different power ratings and 3 different, a short, a medium, and a long distance. But realistically, any number could be put in here. So if you were doing a 37 kilometer line at 150 megawatts, then you could run the solver model and get an optimized solution for those parameters. And we'll do that real quick. And that would be at the 230 kV setting as well at 16.8 million. So that's just a brief overview of the model. And then next I'll show the results from each one of the trials that I ran. This page summarizes the results across each one of the line distance and power that was ran through the model. And the lines highlighted in yellow are the lines that the model selected. So the results indicated that at 10, 50, and 150 megawatts, the power levels across each distance that was evaluated, the 230 kV line is the most economical and optimized choice. And this makes sense looking at a couple of numbers. So the power loss is relatively low because it is a pretty high voltage. However, the structure costs are more similar to those at the lower voltage level. And so on the chart, you can see here in blue, when you shift from the 230 kV to the 340 kV lines, there's a pretty big jump in the costs for those structures. So the 230 kV lines are more optimal for those mid-range, high and medium power needs based pretty much on that structural cost. Now, at 400 megawatts, the 500 kV line was the most economical choice. Now, one thing to call out here is that only one of the 40 conductors, that would be the Bluebird type conductor, passed the minimum conductor size requirements. So at this level, the industry really is limited by what conductors they can use to meet that voltage level requirement. A few other general key points. So the higher voltage lines always resulted in the lowest percentage of power loss. That was across the board. However, just because the power loss was the lowest does not mean that that was the most economical solution. In most cases, the structure-related costs ended up being the largest portion of overall costs. That ranged from 68.4% on the 150 megawatt lines to 90.5% of the 10 megawatt lines. The other piece of the 40 conductors, the model only selected 3 different kinds, and that is really a beneficial thing for standardizing lines, for managing inventory, and for potentially getting the lowest price available when buying in bulk. Minimizing the number of conductor materials that are used across a network means that conductor material is going to be more readily available, and you have the perks of buying in bulk. Now, in conclusion, the intent of this research model was really to build a simplified model to be able to select the best voltage that optimized efficiency through power loss while also looking at the economical side of that solution. I also wanted to be able to show what building in a constraint could look like in a system as simple as Excel. So future models would definitely incorporate some things to make them a little bit more robust and more practical in the industry. First off, additional costs would need to be built in, things like ongoing maintenance costs, the right-of-way land costs, and other parameters just to make it a more realistic model. Second, the lifetime of the asset would need to be considered. So this model factored in 10 years. Rather than 10 years, whatever the expected lifespan would be a great point to build in, or to go out, 20 or 30 years at least. And then lastly, additional constraints could be built in. So in this case, the minimum conductor properties were looked at based on voltage requirements. Additional constraints like strength and sag, corrosion considerations, and then wind and ice could be factored in. Those three things being built into a model like this would really take it to a level of, being able to be used in transmission planning and having decisions based off of it. And with that, I'll wrap it up. I look forward to any questions you have. And again, thank you for taking the time to listen through this presentation. And I look forward to your questions. Thank you.